All right, so 1.2 prime factorization. So we're going to be dealing with greatest common factor and least common multiple. So big skill for this one is something called prime factorization. So last time we were dealing with like factors of numbers, and all we did was we just like looked at the number and said, okay, what numbers can multiply to get that number, right? And we just kind of figured out what they were. So it turns out, like if you get a really big number though, right? Like even like 340 would take a while to figure out the factors of 340, right? So there's little tricks we can do to figure this out a little easier, and it's something called the prime factorization. So here's how it works. So if we want to break 340 into its prime numbers, so remember prime numbers are like numbers that don't go any lower, right? They're numbers that are only divisible by itself and by 1, right? So what we can do is do this like tree method. And how this works, I'll just do it over here too. So you'd start off with 340. And then we want to find any, it doesn't actually matter which ones, but we want to find any two numbers that can multiply to 340. Okay? So a good way, an easy way to look at this too is, let's say you can't think of any. As soon as I know it's an even number, what number goes into an even number? 2. So I know that one goes in, right? So I could just go 340 divided by 2 in your calculator, right? You have your calculators now. And if you weren't sure, you could go, okay, well that's 2 and 170. Okay? And then 170, even number again, right? What number goes into that? 2. Actually, I guess that's not the way we did it here. You could do that, though. It'll work out the same. We could also break this thing into 17 times 10. It would have worked to divide by 2. We would have got the same numbers in the end. And then this 10, I can divide that into 2 and 5. And that's it. The ends of our tree here, those are our prime numbers. You see how all the ones at the end are just as low as we can go? You can't divide them anymore. Those are our prime numbers. So lastly, what we would do is you say, okay, well that means that 2 times 17 times 2 times 5. Anybody know what that would have to equal then? 340. Yeah, it would equal 340. Multiplying all those numbers would equal 340, right? We wouldn't write it like this. We wouldn't write it with 2 times 17 and then times 2 again. We would actually write it like this. You'd write it as 2 squared times 17 times 5. Or times 5 times 17. And so what I mean there is that we take that 2 times 2 part of it. 2 times 2 is the same thing as 2 squared, right? If there would have been another 2, then that would have been 2 to the power of 3. Okay? So that's typically how we write the prime factorization. Okay, so why does that matter? We're going to see that using that prime factorization, we can figure out the greatest common factor and the least common multiple through a couple of ways I'll just show you here in a second. Okay. Can you guys try this one? Find the prime factorization of 72. I'm going to, whether you got there or not, I'm going to carry on this one. So 72. What two numbers multiply to 72? 2 and 36? Sure. 2 and 36. And then 2, that's as far as we can go, prime number. So, but 36, I can break that into, what's that one? 2 and 18, sure, yeah. 2 and 18. You guys might have done something different too, right? Still might be right. 18 can be split into 2 and 9, and then 9 can be split up as 3 and 3. So that's it. So the ends are, those are our prime numbers. So the way we'd write that though would be 2 to the power of 3, because there's 3 of them, right? Times 3 to the power of 2. There's 2, yeah, 2 3s. Okay. Okay, that's the idea. I think for the sake of time, this would be the same thing. It'd just be longer, right? You just divide it by 2 quite a few times on that one. Yeah. All right, so greatest common factor. You guys have been dealing with greatest common factor and least common multiple in other grades too. But what the greatest common factor is, it's the biggest number that goes into both of the numbers, right? It's the greatest common factor, right? So there's several ways to do it. You could just like try them all out, right? So if I want to figure out the greatest common factor, let's say of these two numbers, you could just try some things out. That's essentially what they were doing here, right? So method A is that to figure out the factors of 690. So 5 times 138 gives you 690. And 11 times 138 gives you 15 or 1,518. So that's the biggest number that goes into both, right? That would take a long time and that'd be annoying. So that's why we're going to use this other method. So method B is if we break it into its prime factors using the method above with like the tree thing, and we figured out that our prime factors were those for 690, and they were those for 1,518, then you can see the things that they have in common, right? They both have 2s, 3s, and 23. So that means if those are in common for both, if I multiplied those, then I'd end up with 138. You get up to 138. Does that kind of make sense? They have those prime numbers in common. So 2 times 3 times 23 gives you 138. So that has to be a common factor to both. Yeah? It's magic, yeah. Okay, so let's do our own here. So it says find the greatest common factor of 152 and 190. All right, so we'll break it into its parts here. So actually I'm gonna write it out again. So 152. So 152 could be written as, or what are the two factors for that one? 276. Yep, 2 and 76. Okay, 76.
38.
So 2 and 38. Oop. It says potential fraud.
Do I need to take your phone?
It didn't answer it.
But you dropped it.
And just drop it.
I dropped the call.
Stop. Stop.
Time to stop.
Okay. Oh, I was recording all that. Okay. All right, so 38 can be broken up as, so 2 and 19. 19, nothing, right? That's it. So I'm going to write that one out. That's going to be the same thing as 2 to the power of 3 times 19. Okay, and then we'll do the other one. So 190 could be 2 and 90, yep. Oh, sorry, 95.
Yeah. 95 right.
Okay, and 95 can be broken up as 5 and 19. So it looks like that's it. So all we can do here is 2 times 5 times 19. Okay, so greatest common factor. Yeah, so just remember here too, I've written this as 2 to the power 3, but that also would have been like this. 2 times 2 times 2 times 19. So all we can do is like take one of those 2's, right? That one, and then the 19 and the 19. Right? So the kind of the rule here, if you were looking at this one, is if a number shows up, you write it down. So a 2 shows up, and then you take the smallest power. So this was like to the power of 1, so it's just the 2. Does that kind of make sense? And then we'd multiply that by, well, 19 shows up in both. So it's going to be 2 times 19. Okay, so what's the greatest common factor here? 38. How you guys doing? Is that kind of making sense? Yeah. Okay. All right. Least common multiple. So this gets a little bit confusing because greatest common factor. Just notice that we ended up with a small number, right? Greatest common factor. We ended up with a number smaller than both of those numbers. And now we're going to look for least common multiple, and actually we're going to be finding a number bigger than both of those. So it's like the wording is different than you think. So least common multiple is the first number that they both go into. Right, so that's our least common multiple. So we want the smallest number that they both go into. But the least and greatest always throws kids off because I think when they see the word greatest, they think they're looking for a big number. And when they see the word least, they think they're looking for a small number, but it's the opposite. Okay, so least common multiple is the, oh, that's what I said there. Okay, so we could write it out. That's what we did in the last one, right? So for 8 and 6, if we were to find those, then you could just keep writing out numbers until you find where they overlap, right? So it goes 6, 18, 24, 6, 12, 24, right? If you had 3 numbers, it becomes even less likely to find them though. So I really don't recommend doing this approach if you have 3 numbers. This one wasn't too bad. You could keep going up by 12s, 15s, and 40s, and the first one that repeats is 120. But sometimes, like especially if you use 3, you're not going to get a repeat for a long time. So you might write out like an entire page and you still might not get a repeat, right? So this method would be a long one. I wouldn't recommend that. Okay. The second method is again to use our prime factorization. So there's an example there, but I think let's just do the one below to, I'm not going to try the first method. So we'll do 15, 32, and 44. So the first number that they all go into. So we got to break them all into their primes. So 15 could be broken down as 3 times 5. That's it. 32 would be, what do you think? 2 and 16. 16 would be 2 and 8 would be 2 and 4, and then 2 and 2. Okay, so sorry, this first one was 3 times 5. This one would have been just 2 to the power of 5 in total. Yeah, 2 to the power of 5. And then 44 can be split up as, so 2 times 22, and then 2 times 11. So that one would have been, could be written as 2 to the power of 2 times 11. Okay, so now what do we do with these? So when you're finding the least common multiple, if the number shows up at all, right, so in either one, we're going to write it down. So a 3, or I'll do a 2 first. So a 2 shows up, so I'm going to write it down. A 3 shows up, so I'm going to write it down. A 5 shows up, and then 11 shows up. And then we actually have to take the highest exponent in this case, because the numbers have to go into the biggest one. Like it has to be, if that makes sense, they all have to go into the biggest one. So we have to actually take the, when we looked at the 2 to the power of 5 was the biggest, so it's got to be 2 to the power of 5. Make sense? So then we have to multiply all of those out. So whatever that is. Anybody know? So 5,280. All right, so you guys are probably getting the sense. If I would have just written all that out, that would have taken forever. Yeah? Okay. Okay. You guys have a question like this when you get going too, so I'll go through this one. So it says, at Fritz Flooring, the whatever style of tiles measures 20 by 36 centimeters. Assuming the rectangles cannot be cut, what is the side length of the smallest square that could be tiled? You may want to check, yeah, so there's an example there. So here, the problem with this question, it's actually not that hard a question, it's figuring out what we even need to start to do here, right? So I'm going to just draw this rectangle. And it is going to be 20 by, here I'll do 36 on the top, 20 by 36. Okay, so what the question is asking is it's saying if I tiled this thing with squares, what is the side length of the square? So like x on both sides there, what's the side length of that square that would tile that thing perfectly? Right? That would just be, it would just fit perfectly into that side and fit perfectly into that side all the way across, so that we don't have to cut any of these square tiles when we get to the end here. Anybody know what we got to do? Or what we're actually looking for there? Yeah, we're looking for the first number that goes, or sorry, the biggest number that goes into both of them. We're looking for the greatest common factor. Right? So you might be able to do this one in your head. What do you guys think? What's the biggest number that goes into 20 and into 36, right? 4. So 4 goes into both of them. So if you just know that, right, that's the biggest number that goes into both, great. But we could also break it down. We could say, okay, 20 can break down as 4 times 5. 36 can be broken down as what? 2 times 18, and then 2 times 9, and then 3 times 3. Okay, so then, oh, sorry, and then 4 was 2 and 2. Okay, so what's common to both? 2's, those 2's, right? So that'd be like 2 squared times 5, and this would have been 2 squared times 3 squared. So the 2 squareds are common to both, so 4. Okay. All right, 7 says simplify these. So you guys could probably simplify these anyway, but we're just going to kind of use the method that we just learned there. Can I get you guys to break down 340 and break down 380 into its prime numbers? So what do we get? So, all right, so 340, let's break this one up. What do we get? So 340, we can break that. 10 and 3 is what you did? Oh. 2 and 170. 170, what was the next one you guys did? 2 and 85? 5 and 17. Okay, cool. Okay, 380, what did we do? Okay, 190 would be... Yeah, and then 95 would be 5 and 19. Okay, so why I said we should do that is because now if we, instead of writing 340 over 380, if we actually just rewrite that instead with our prime numbers, then we can actually cancel these things pretty easy. So we'll go, instead of well here, I'll go 340 over 380. Well, that's just equal to what we just found. 2 squared times 5 squared. No, sorry, just times 5 times 17. And then the bottom one would be 2 squared, right? 380 is 2 squared times 5 times 17, or times 19. All right, so watch this magic. You got 2 squared on the top, you got 2 squared on the bottom. They cancel with each other, right? 5 cancels with 5. So all of that simplified just down to 17 over 19. Magic.
So why can't you just do the 2?
Yeah, so like I was saying there, we could have just like simplified, probably like you guys are more used to. But this way of like simplifying like the factors of it and just canceling out those factors, that's like a more advanced math thing that we're going to be doing more and more, right? Math 10C, 20-1, 30-1, like we do tons of that, but with variables and everything too. So.
Why do you have to do all the extra stuff? Can't you just write 17 and 19?
Okay, so I'm going to skip through question 8. The idea is, you guys have been doing this forever, when we add, well, actually, you know what? It's probably worth doing. Everybody forgets adding fractions anyway. Okay, so 9 over 14 plus 11 over 16. So you're 9 over 14 plus 11 over 16. All right, so how do we add fractions? What do we do again? Yeah, you have to find a common denominator, right? So really what I'm asking here is, what is the first number that 14 and 16 both go into? What's another way of wording that? I'm looking for a least common multiple between 14 and 16. Okay, so what do you guys think? Least common multiple between 14 and 16. We might be able to do it in our head, but if not, we can do our little system there, right? Yeah, let's go. So 14, let's break it down. So 14 would be 2 and 7. 16 could be broken down as 2 times 8, and then 8 would be 4 and 4, or 4 and 2, sorry, 2 and 4. And then 2 and 2. Yeah? So this was 2 times 7, and this one was just 2 to the power of 4. Okay, do you remember the rule for least common multiple? If the number shows up, we just write it down. So a 2 shows up, and a 7 shows up. And then I take the biggest exponent, if there's an exponent on them. So that's going to be 2 to the power of 4 times 7. No, I'm using my calculator. Okay, so that's going to be
Wait, what's minus
112, right?
That's one easy thing cheat.
Oh, shoot.
Yeah, but like, how do you
Okay, Kevin, focus. 14 and 16. All right, so what we're going to do is we're going to write this as something over 112 plus something over 112. Okay, so then I got to figure out, okay, what did I actually have to multiply 16 by to get to 112? Yeah, let's just go 112 divided by 16 to make life easy. So 7, right? So I had to multiply that by 7. And you have to multiply the top by 7. Okay, so 11 times 7. Yeah, right, so 77. Okay, and then on the other side, what do we have to multiply the 14 by to get 112? 8, okay, so 8. So we have to multiply the top by 8. So that would be 8 times 9 is 72. Okay, so in the end, we get 149 over 112. Phew. Okay, you know what? For this nasty question of the day, I'm going to leave that one. It actually ends up being a lot like this question, but in 3D. Well, no, we could do it. I might make like a video of it, or we'll do it after, just when we got some more time. But all right. So 1-3 squares, cubes, and roots. So good news is we kind of did this in Math 9. This is like, you guys remember the square root unit in Math 9? You hated that? Yeah. Yeah, so more of that. So if you remember where this idea of a square root comes from, if I had a square, like literally a square, right? And one length was 3 and the other length was 3 because it's a square. And I wanted to find the area of this, what would you do? You'd go 3 times 3, or 3 squared is equal to 9. Okay, and if I want to go backwards, right? So if I had the area and I wanted to figure out what the side length was, then I would go, well, what would you do? You go 9, you'd go square root of 9, right? Square root of 9 is equal to 3. Okay, so that's the idea here. So we've got our perfect squares that we can keep in mind. So you've got, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, and they're still all up there, right? There's those perfect squares up on the side there still. Okay. Yeah, pretty much it. Okay, so it has right the first 12 perfect squares and there's square roots. I think we'll be okay on that one. I think I'm gonna skip past that one. Okay. Example 1. So we can find the square root of something like 576 using estimation or prime factorization. So we could estimate, using those benchmarks to kind of figure out where we were, and just to kind of like trial and error some things to figure it out. Typically that's probably what you're going to do, if I'm being honest, that you'll just kind of like go, okay, what is 23 times 23? What is 24 times 24? Until you get to that number, that might be what you do. The other way though is we can do the prime factorization of it. So if we broke 576 into its prime numbers, then what we can do is we can rewrite those prime numbers as long as they're symmetric, like we have 2 of each, right? So if we can write this out as 2 times 2 times 2 times 3, and then have exactly the same thing on this side, 2 times 2 times 2 times 3, then that means that that's a perfect square. And if I actually just go 2 times 2 times 2 times 3, that's 24, and then times itself again, so the square root of 576 must be 24. Did you guys follow that train of thinking? Okay, we'll work on it. Okay, let's try with this one. So let's go 1296. Can you guys right now, this will be good practice, let's do the prime factorization of 1296. So do our tree thing. right? Did you guys get something like that?
Yes. Oh, I got it. I went from 81 to 27.
Okay. It worked out the same probably though, right? Where you got all threes in the bottom?
Yeah.
Yep. Perfect. Okay, so let's write this out just with the numbers instead of as a tree. So we'll say, well, that's the same thing as 2 times, well, actually here, we'll just count them. So we got 1, 2, 3, 4. So 2 times 2 times 2 times 2. And then times 3 times 3 times 3 times 3.
Or we could just do 2.
You could, yeah, you could. I just kind of want you to be able to see what we're going to have going on here. So the idea here is I want to have this written as something times something else, right? If I can make those both exactly the same thing, then that's going to be a perfect square, right? So let's go. Okay, well, what if I go 2 times 2 times 3 times 3 on this side? So that accounted for 2 of the 2's and 2 of the 3's. And then these ones on the other side. So 2 times 2 times 3 times 3. So yeah, it looks like it's a perfect square, right? Like this times this gives me 1296. So 2 times 2 times 3 times 3, what is that? 36. So that's the same thing as 36 times 36. So what is the square root of 1296? 36. Yeah? Okay. Yep. With the 9s there? They weren't the end of my tree, so I'm just going to ignore them, right? When I'm looking at the prime numbers, I'm only looking at the ends of the branches. All right. Perfect cubes and cube roots. So any number that can be represented as the volume of a cube, but the whole number side length is a perfect cube. So what I mean by that is if you had a cube, blow your guys' mind. Okay, so is that so remember volume. Volume is equal to length times width times height. And if we're dealing with a cube, then the length, the width, and the height are all the same thing, right? So if this was, let's say, 3 by 3 by 3, what would the volume of this be? 27, right? 3 times 3 times 3 will give you 27. So we'd say 27 is a perfect cube. Yeah, because if you take the cube root of 27, what do you think you get? So cube root is like a square root with a little 3 on the front. What do you think you get? Cube root of 27. 3. Yeah, you get 3 out. So it's like the same idea as square roots, right? Okay. So so first 10 perfect cubes. Yeah, can you guys do that? I'll pause it here. Okay, so what's the first perfect cube? It's actually kind of a bit of a trick question. What's 1 times 1 times 1?
1.
Yeah, so 1 itself is also a perfect cube. So it's going to be 1. And then 2 times 2 times 2? 8. So here, let's go 1, 8. What's the next one? 27. 3 times 3 times 3. 4 times 4 times 4, or 4 cubed. 64. Anyone know any other ones? 125. Let's do like one more. What is it? 216, right? Good enough for now. The big thing is I just need you guys to be able to find those perfect cubes if you need to, right? Like in your calculator, that's how you can find them to figure out what the perfect cubes are. So you can memorize some of these. Typically we're using like, you know, the smaller ones, but you might have to be able to tell if some big number is a perfect cube, right? So, okay. So we can do the same little trick here with prime factorization. I'll just show you that again. So can you guys do the prime factorization of 1,728?
Mr. Brown?
You guys are gonna get tired of this prime factorization thing, but you're gonna know it.
When something is squared by 0, it's 0, right? Or is it 1?
It's 1. Anything to the power of 0 is
Yeah.
1.
So is that the same with cube? Cube?
Well, it wouldn't be to the power. It wouldn't be cubed if it was to the power of 0.
Whoa.
Did you guys get all of those prime numbers?
Now I'm moving back.
I got 1, 2, 3, 4, 5, 6 twos and 3 threes. Okay, so if we want to figure out what the cube root of this is, same type of thing as square roots, right? But instead of having like something times itself, right, just the two of them, if it's a perfect cube, yeah, it should be 3 of them, right? It should be the same thing for all 3. So we should be able to say something times something times something is equal to 1728. So I just gotta like divide these 2s and 3s up so that I got even amounts in each. So
You don't give us enough room to do this. Yeah.
just zoom in like I'm doing.
Just zoom in.
Yeah, just kidding.
Oh my god, why didn't I think of that?
So 2 times 2 times 3.
Paper, right?
No, you gotta get glasses that like magnify glass.
Okay, so if this is the case, right, if I was able to just rewrite all these 2s and 3s into like even amounts for each, what would the cube root be then? Yeah, 12, right? Because it's going to be 2 times 2 is 4 times 3 is 12. This is the same thing as 12 times 12 times 12. Which would be equal to, yeah, 1728. So the cube root of 1728 is equal to 12. So for the most part, guys, you will just go cube root in your calculator to find the answer. But this idea of splitting it up, it's kind of like a conceptual thing. So sometimes you might get a question where like it's written all funny like this, and you need to know that just this part of it would be the cube root, right? So, but that's you're not gonna. I don't expect any of you guys to actually do this when you find the cube root of a number. You're probably just gonna go the cube root of that. Okay. Radical symbols. So, okay, so radical is just this symbol, right? So this is like a radical. And so that could be so far a square root, a cube root. You can have a 4th root, a 5th root. You can have any root you want, right? A square root, though, typically, like you could write it like this with a symbol and then a 2 on the end of it. But since square root gets used so often, this is what you guys are used to too, is it's just the symbol itself. So we just forget about the 2. But it's implied that it's a square root. Different parts of the radical. The symbol on top, so like on a cube root, this is called the index. So we have an index of 3. The radical is the actual like symbol itself. And then the number underneath, so if this was like 27, the number underneath is called the radicand. Radicand, yeah. Okay. Yeah, and you guys can kind of read through this if you want. So these should be gimme marks too. Like if you guys have like any quiz questions or test questions where it says these ones, this is just like a definition type of stuff. So what are the index and radicand for each of the following? So let's look at this first one. What's the index for this one? 3, right? What's the radicand? 4. Okay. Yeah. What about this last one though? What is the index for this one? 2. It's actually 2. Even though it's not written there, there is like a invisible 2 hanging out there. Okay. All right, so this is exactly what we did in Math 9. So it says estimate the following to at least 1 decimal place. Square root of 81. Yeah, square root of 81 is equal to 9. If you were putting this in, like on my open math, if I said 1 decimal place, you'd have to write 9.0. Because that's 1 decimal place. Okay, the square root of 52. How can we figure this out without a calculator? I'll give you a hint. I'd probably look at... So square root of 52, 7 point something, right? And what you were just doing there is we know that the square root of 49, right, is 7. And we know the square root of 64 is 8. Okay, so the square root of 52, so that's like right here, close to this one. 7.2? Yeah.
7.2. That's what the calculator says. Wait, how do you do like cube root?
On your calculator?
Yeah.
I'll show you after. It's second, and then I think the square root symbol does it.
Cube root.
Yeah, but
All right, the cube root is 64. So those ones aren't up there.
Oh.
So yeah, something. So it's 4 times 4 times 4 gives you 64, right? So 4. The cube root of 52. Okay, so this one might be a bit tougher. So we got to write out our perfect, not squares, but perfect cubes now. So here, let's write out a few. So there's 1,
is it 29?
8, 27. What's the next one? 64. Okay, so we want 52. So it's between. So if I know the cube root of 27 is 3, and the cube root of 64 is 4, then the cube root of 52, yeah, 3.6, sure, close enough. What'd you get? Did you get 3.6 when you put in the calculator?
I don't even know
What
how to
the heck is a fourth?
A fourth root?
is to
Okay.
power 4.
So let's do like write out for the fourth roots to figure this one out. So 1 times 1 times 1 times 1, right? Or 1 to the power 4 is 1. 2 times 2 times 2 times 2 is 16. And then 3 times 3 times 3 times 3 is, anyone know? 3 times 3 times 3 times 3. The easy way to do this is 3 times 3 is 9. Those 3 are 9. What's 9 times 9? 81. Okay, so 52. So we know that the fourth root, so fourth root of 16 is 2. And we know that the fourth root of 81 is 3. So I gotta be thinking 2 point something, right? So then 52, 2 point, sure, yeah, 2.5. I'll show you in the calculator after. All right, so that's it, guys.